Our next speaker is, surprisingly, a true plastic advocate. Her accidental invention of a super strong and fully biodegradable polymer might actually make today's environmental curse tomorrow's sustainable answer. Recyclable airplanes, dissolvable water bottles, and dramatically diminished landfills, these are only some of the implications, it seems. The most enthusiastic female chemist just so happens to be one of the amazing speakers at today's Reactions Conference. Please give a warm welcome to Dr. Janette Jamie Garcia.
Thank you. Thank you, Emma. And thank you to everyone for your kind attention today. I'm going to talk to you a little bit about the work that I've been doing in recyclable polymers. So I wanted to talk very quickly about some of the work going on at IBM Research, which I am a part of. People are oftentimes very surprised to hear that there is any chemistry or polymer chemistry occurring at IBM, which is known for computers. So just to give you an idea, we have 12 research labs across the world. In these 12 labs, we have some of the best scientists, and they range in a variety of different disciplines. The closest to here probably being our Zurich labs. I'm actually currently at our New York labs, which is our Watson. It's our headquarter and our gem of research. Most of the work I'll be talking about today was actually done in San Jose, California at our Almaden Research Lab. Almaden is well known for its polymer chemistry, and the polymer chemistry originated in semiconductor research that we've been conducting there over decades. We're interested in very large problems, and I am interested in very large problems. So some of them are listed here, such as healthcare, education, security, commerce. But mainly, I'm interested in energy and environment. So creating new technologies that will both help energy and help preserve our environment. Being able to tackle world's large problems takes a wide variety of different disciplines and specialties to come together. So therefore, I work with a dynamic range of scientists, everyone from biologists to physicists to chemists like me. So my background is actually in small molecule organic chemistry. My PhD was based on working on and designing catalysts to break and form bonds on a very small scale. I was drawn to IBM because they were using the same catalysts that I was looking at and studying during my PhD to both build macromolecules and make polymers such as the ones you saw earlier, and also, and this was new to me, to take them apart. Therefore, I'm going to talk a little bit today about the work we've been doing on engineering polymers from secondhand materials. So here's the crux of the problem. There is substantial value to be gained by learning to recycle our synthetic materials. We produce about 300 million tons globally per year. We create about 150 million tons of plastic solid waste just in our households alone. We can save over 100 million kilojoules of energy if we were to recycle this plastic waste. If you crunch the numbers and actually figure out what this looks like in terms of crude oil prices, we have the opportunity to save $176 billion globally if we were to figure out ways to adequately address this problem. 30% of plastic is recycled in Europe. You're doing a lot better than us in the US. We recover 8.8%. From that 8.8%, you then can either recycle, incinerate, or industrially compost. So this number doesn't reflect recycling values. In Europe, you incinerate about 40% of plastic to regain energy. Thus, this quote makes a lot of sense. It's from a book called Natural Capitalism, and it says that the flow of molecules in the US economy is 98.98% pure waste. Correcting this is the biggest business opportunity in the history of the global economy. So a lot of times when I read this and when I talk to people about the statistics, they shake their head that this cannot be true. But if you think about the ways that we typically handle our materials and dispose of them at the end of life, they all have a natural progression towards true waste. It has led to severe environmental problems, such as this shown here. This is the representative of the Great Pacific Garbage Patch. This literally occurs because landfills are overflowing and waste is leaking into our oceans. It's expected to double the amount of waste in oceans by the year 2020. By the year 2050, 99% of seabirds will contain plastic in their bellies. They take pieces of it that they see floating in the ocean, mistake it for food, and ingest it. It's also led to images such as this one being popular online and creating a very negative feeling about plastic and its impact on the world. This turtle has clearly grown up in its polyethylene soda six-pack ring. This six-pack ring would take 500 to 1,000 years to decompose naturally. So, the future is looking grim. Or is it? Are there ways that we can actually address the problem with plastics by taking an alternative approach? It makes a little sense to first go through what the common approaches are currently. So there's 4 different ways that we handle plastic waste. They fall into these categories. They are primary, secondary, tertiary, and quaternary. Primary and secondary are both mechanical recycling processes that require that you physically break the material down, shred it, decontaminate it, and then melt it and remold it back into plastic for use. Quaternary, or energy recovery, is also incineration. So this is where we burn the plastic and then take the energy in the form of heat. This is extremely convenient because you don't have to separate or pre-sort plastics into pure feedstock. You can just do mixtures and it doesn't make a difference. However, you can't regain in this process the most valuable starting materials, which are the monomers. And chemical structures and bonds that we've so carefully placed in to have the polymer structure and properties that we're desiring are destroyed. Tertiary, or chemical recycling, currently is known for essentially thermalizing or pyrolyzing polymers in their melt state above inorganic catalyst. So when you do this, you can break the material down into lower molecular weight materials such as waxes and fuels. However, because you have to do it in the melt state, temperatures required for this are around 300 to 500 degrees Celsius, which makes it energy intensive and unfeasible for industrial use, typically. So the basic process then is that with our polymer waste, we take our raw materials that are petroleum-based, we do some sort of processing or chemistry on them to make our monomers. Our monomers are then turned into polymers through a chemical process. They then are used maybe once or twice before you dispose of them. They turn into waste materials, and at the end of life, they either go to landfill or in some cases, they undergo a mechanical recycling process. This mechanical recycling process closes the loop from your waste materials back to the polymeric materials and goes through this cycle probably only 2 or maybe 3 times before severe polymer degradation occurs. After that occurs, the polymer is no longer viable for its initial intensive use, and then it ends up going into the landfill ultimately, or into some other type of material which can no longer be recycled. An example of this is going from polyethylene terephthalate, or PET, down to your materials for your carpet. So if you were to figure out a way to make chemical recycling a little bit less energy intensive, what we could do as chemists is actually target the weak bonds in the polymer structure and be able to take waste materials, break them back down in a chemical method, which was how they were produced in the first place, to gain the precious monomer starting material. This monomer starting material has the functionality built in order to make the polymer in the same way that it was in the first time, and then go on to close the loop, and if done efficiently, this could be a truly infinite process. So, some examples of that are shown here, and this is some of the work that we've done at IBM. So one thing that we were very interested in is, could we take e-waste? So I show it here in the form of CDs. CDs are a complex mixture of materials, so they commonly have polycarbonate as being the plastic material, and then a layer of aluminum, which is what gives it that shiny appearance. So what we were able to do is take polycarbonates, which have weak carbonate linkages in the polymer backbone, target those polymer linkages with a catalyst, break it down to monomer in one pot, and then rebuild a polymer out of it that has a higher value than the starting material. So in this case, what we were looking at was polysulfone. Polysulfone is an engineering thermoplastic. It's well known for use in high temperature requirements. So things like high temperature medical equipment, for example, is made out of polysulfone. And in addition to that, it has a very high degree of toughness. So it's also used as backing in things like reverse osmosis membranes for water purification. So this is an example of where we were using essentially what was waste, cutting it down into pieces, and then using it as a latent monomer source, so basically a hidden source of monomer for the synthesis of a new material, and it could act as a drop-in replacement. In addition to that, we've also done some experiments with PET. So PET is polyethylene terephthalate. It is what our water bottles are made of. We have an abundance of water bottle waste. We were able to develop catalysts to break this down, and you can do two things with this waste. You can either go back to monomer, so you can depolymerize it, regain your monomer so that you can make water bottles again in a true closed-loop fashion. Or, because we could tune the properties of the chemistry that was occurring, we could take the PET waste, apply a catalyst to it, and make a different type of monomer. With this other type of monomer, we could make new high-strength materials. So high-performance either thermoplastics or high-performance thermosets. So the difference between thermoplastics and thermoplastics have a melt state typically. They're usually linear chains. Thermosets are more like a cross-linked fence. So they're an array, a 3D array of molecules linked together. Thermosets represent some of the world's strongest plastics. They're also what are used in a lot of structural composite materials, like something that you might use for an airplane wing. So I'm going to tell a quick story. It was my first week in the lab at IBM. I had not done any research yet in the polymer space. I'd only been working with small molecules, which are, by default are easier to work with because they're soluble in almost everything. I had the job of trying to make a thermoset from some of the PET waste that we had collected out of the cafeteria earlier that day. I set up my reaction. I needed to add 3 things into the flask. I added 2. Walked away to gather my 3rd, started heating, came back to the flask, and it had completely hardened. So there was this solid mass of material in the bottom of my flask, which I then tried to break apart, and I couldn't break it with a spatula. I had to break the flask in order to recover the material. Once I recovered it, it was insoluble in everything. So I went to my professor, the person that was guiding me during these experiments, and I said, "What did I make?" And he goes, "I don't know. Better figure it out." Okay, great. So 9 months of experiments and characterization later, really pulled in some of the expertise of my fellow colleagues to try to figure out what I had made. I found out that I had made a thermoset material. That thermoset, as we were testing it to figure out what it was resistant to chemically, we tried oxidants, we tried bases, we tried acids. It was resistant to both the oxidant, it was resistant to the base, but in acids, it turned out that it completely depolymerized back to its starting material. I unknowingly had come across one of the first examples of a depolymerizable thermoset material. So I'm going to show you a video of how this process works. So essentially what you're going to see in this video is there's going to be 2 different types of materials added to it. The first one is a common rubber material. The second one is the thermoset that we discovered that day. And what you'll see is that as it's added, it completely dissolves. whereas the rubber material is completely untouched. It takes about 12 hours to completely react. You then get a clear solution, which you can neutralize in a basic solution. When you neutralize it, there's a precipitate or a cloudiness that occurs. And what that cloudiness is actually pure monomer. We then can filter the monomer, very easy to do, collect it. And then once we have the monomer, we can use it to repolymerize. We can either repolymerize it into the same thermosetting material or into something else, like a polyimide. So what essentially you've seen here is we've taken a material that is stiffer than bone in its polymerized state and broken it all the way back down to the precious monomer just by soaking it in acid over time. In addition to that, we could use the same chemistry and the same reversible chemistry to look at different types of materials and access different really interesting properties. So if we switch out the monomer for something that is a little bit higher molecular weight, so it's more like a piece of spaghetti with functional groups on the end, a longer monomer, we can form organogels. So this is a picture of the organogel. You'll see that there's a blue stripe and a white stripe. So essentially what we've done in this case is we've made two different gels in two different batches. One had a blue coloring to it. The other one was just clear. And then we cut them both in half and put them back together just by touching an alternating sequence. When you pull on the material, which is an elastomeric material, what you can see is that has instantaneously self-healed. So the places where the two polymers had touched together have now come together to form one cohesive unit. This reaction is reversible as well, so it's also a recyclable material, but you can think of it as having very different uses. So instead of airplane wings, for example, we might make reversible adhesives out of this self-healing material. So there's still some challenges to be addressed here. I've shown the work that we've done on polycarbonates and polyethylene terephthalate, both of which have weak links, if you will, in their backbones. The future of chemical depolymerization and chemical recycling is really going to lie in technologies that are developed for treating things that are very difficult to recover and recycle currently. Things like polystyrene foam, which has a different density than its parent substance, so it's very difficult to sort in sorting facilities. Things like packaging, which constitutes a massive amount of the landfill waste plastics that we currently have. And then finally, things like rubber tires that are actually composites and mixtures of materials. If we can address these challenges, and I think we can with chemical recycling, then the future of recycling is bright. And with that, I'd like to thank you for your kind attention today.